lecture 16. Last class I was talking about stress in a fluid medium. I'll continue with that. However, before that I want to make a clarification. I got some feedback from today's tutorial session that some students were having difficulty understanding how to use the continuity equation to predict rate at which density changes following a fluid particle. Now this is the continuity equation that we derived on Wednesday. How did we derive this equation? Yes, to derive this equation I used a control volume like what I have here. I started with a cuboidal control volume. However, the volume of that control volume, so X is the centroid of this control volume. I called it point Q. I applied Reynolds transport theorem for this small cuboidal control volume. However, eventually in the last step, if you go back and look at the derivation, delta x1, delta x2, delta x3 all cancelled out. And the equation that we got finally is presented here. Pay attention to this equation. Every quantity here, whether it is density or velocity or the derivatives of density and velocity, they are all at same point Q. Same point Q. All these are at point Q. Now if I go to another point, say here, let me call it Q prime, I can again make a small control volume like this, having the same dimension delta x1, delta x2, delta x3. I can repeat the derivation process. What will I get? I will again get the same equation, but at that time it will be at Q prime. What does it mean? It means that the equation that I derived is applicable for each and every point in the flow field. And it has become independent of the control volume that I used to have this derivation. There is no delta x1, delta x2, delta x3, right? So this equation, once derived, should be looked at in an independent manner and need not be associated with a control volume necessarily. Control volume is a step to get to this equation, but this equation is true at each and every point. Since this equation is true at each and every point, let's examine the left hand side of this equation and recognize that the left hand side is nothing but the material derivative of density. That's what I have written here. This is the material derivative, rate of change in density following that fluid particle which is at x. So for derivation I use control volume, but the equation that I am getting, it is applicable for a point, a fluid particle. And since it is applicable for a fluid particle, I write this kind of language. The left hand side is what I have written, and right hand side I have, according to the equation, it is minus rho times del Vi del Xi. That's what I'm showing here in the diagram, that once the derivation is over, this equation is telling me that if I focus my attention on this fluid particle here, which is at position vector x at time t, I measure density of this at time t. Then this fluid particle at time t plus delta t goes to a special point, which is v delta t away from its original position. You make second measurement here for density. So second measurement minus first measurement by delta t, limiting value delta t going to 0. That's what you are getting on the left hand side here. Okay. In the assignment, we are asking that question. Find the rate at which density changes following a fluid particle, which is at location x and time t. You can use this equation without worrying about the control volume. The significance of control volume is gone. It has no relevance. The equation is true at each and every point, as I said before. I hope it clarifies. If not, then students can come and talk to me. In fact, on Monday, I will keep an office hour. If students want, they can come and discuss their doubts with me. I'll make an announcement on Moodle soon. Now let's go back to where we were. To represent surface forces properly, we introduced the idea of the stress tensor, and I was explaining the meanings or the definitions of various stress components. So in this diagram here, what I have done is I have taken the bulk of the fluid, divided it into two imaginary halves, using a plane, a cutting plane, which has its unit normal in plus E1 or minus E1 direction, like this. After cutting the bulk into two halves, if I go to the left half, I identify a point P, and that P has coordinates x1, x2, x3. The unit normal on this face is plus E1. Unit normal on the right half will be minus E1. Then I take a small area which has its centroid at P on the left half, and I ask this question: what is the force that the right half was exerting on the left half when they were together? I am writing that force as delta F1, delta F2, and delta F3 as three components of that force. So these are components of the force that the right half exerts on the left half. Mind you, the right half exerts the force on the left half everywhere. Wherever there was contact, it would exert forces everywhere. In general, that force system will be a distributed force system, and it will change with location. The force here will be different from force here. I am focusing at point P, and I am taking a small area around P, and it is reasonable indeed that we say that on that small area, the distributed force exerted by the right half on the left half would be uniform. And since this approximation is reasonable, that the force distribution is uniform, I can replace that distributed force on this area, by a single force vector whose components are delta F1, delta F2, delta F3. So if you go back to your APL 100 notes, you will be reminded that if we have a uniformly distributed force acting on an area, you can replace that uniformly distributed force system by a single force, one single point force, acting where? Acting at the centroid of that area. You can go back and check. That's what we are doing here. So on this particular patch, there is one single force vector with three components. Now, according to Newton's third law, if you go to the right part and then ask the question, the force that the left part must be exerting on the right part through that small patch of area centered at P, that will be equal and opposite. So if delta F1 is acting like this on this side, delta F1 will be opposite, and delta F2 is also opposite compared to this direction, and delta F3 is opposite to this direction. Okay. Now with these delta F1, delta F2 and delta F3 small force components, this is how some of the components of the stress tensor at point P are defined. Some of them. There are 9 components because it's a second order tensor. 3 of them are defined the way I have written. Pay attention to this. Sigma 1 is limiting value when delta A goes to 0. You make the area as small as possible. Then delta F1 by delta A is what we call as the 1 component of sigma. 1 component of the stress tensor at P. 1 component. Component of stress tensor at point P. Sigma 1 2, the 1 2 component is defined in this manner, and sigma 1 3 is defined in this manner. So with same delta A, I get definitions of 3 of the relevant components of the stress tensor at point P. I have written some points here. Clearly, the first index of a stress component is same as the index of the unit vector normal to delta A. See, in all these three, the first index is 1, and that is being decided by the unit vector E1, E2 or E3, which is perpendicular to the surface or the plane with which you cut the bulk into two halves, and then analyze the forces on one of the halves. Okay. On the other hand, the second index of the stress component is the same as the index of the corresponding force component. This index. So this is going and sitting here. Second index is about the force direction. First index is about the unit vector, which is perpendicular to the surface with which you separated the bulk into two halves. Convention, this is how it is defined. The sign, whether plus or minus, of the scalar component of the stress tensor is determined based on both the direction of the force components and the direction of the outward normal vector of delta A. There is a sign convention involved here. Now, if it is a scalar component of a vector, we know the sign convention. If delta F1 is positive, it means that the force is along plus E1. If delta F1 is negative, we know that the force is along minus E1. So only the direction of the force component decides the sign. But in stress tensor, the scalar component gets its sign not based on one thing, but two things. Those two things I am explaining here. The sign of a scalar component of, say, sigma ij, where I and j can be anything between 1 and 3. The sign of scalar component of sigma ij of the stress tensor is positive if the outward normal is along plus ei direction, and the scalar force component delta fj is also positive. So both the unit normal, outward unit normal, outward unit normal. See, both are outward unit normals. If the outward unit normal is along plus EI direction and the force is also along plus EJ direction, the sign of the scalar component of sigma EJ will be positive. The sign of scalar component of sigma ij is positive, again positive, if the outward normal is along the minus ei direction and the scalar force components of delta fj is also negative. Still it is positive. Which means that if you try to define sigma 11 using the left hand side, the way I have drawn the forces, sigma 11 will turn out to be greater than 0 if you focus on the left part. But even if you focus on the right hand side part, please keep your mics on mute.
3 और 4 दोनों में होता.
Even if you focus on the right hand side part, what is happening is delta F1 is negative, but the outward unit normal is also along minus C1. And thus, even if you try to find the sign of sigma 11 based on the right hand side, right half of the bulk, you will still get a positive sign. That's what these two rules mean. These are rules we have made for ourselves. The sign of a scalar component of sigma ej of stress tensor is negative if the outward normal is along plus ei and the scalar force delta fj is negative. And finally, the sign of scalar component of sigma ej is negative if the outward normal is along minus ei and the scalar force component is along positive direction. Okay, so if both normal and force positive, then sigma gets positive sign, the sigma component gets positive sign. If both are negative, even then it gets positive sign. But if there is a mismatch in between the signs of the outward unit normal and the force direction, there is a mismatch in sign, then the sigma component, that sigma component will have negative sign. I have explained this already. Let's move on. On the previous slide, I could define three components of the stress tensor. To define the next three stress components, I need to cut the bulk of the fluid in a different way. Now I am cutting the bulk of the fluid using a plane which has its outward normal like this along E2. Not outward normal, a plane will not have outward normal. I would say that a plane which has its normal along plus minus E2, whichever you take. But then it is vertically up as shown in the, it's vertical. Up or down doesn't matter, it's vertical as I have oriented the figure. So you cut the plane, cut the bulk into two halves, you get an upper half and you are getting a lower half here. And the way I have cut it, make sure, please pay attention that the cut still goes through the same point P. This point P is the same that I had on my previous slide. Why? Because I'm talking about sigma at P, which has coordinates x1, x2, x3. Yeah. Once I get two freshly cut surfaces, again I take small areas there, delta A, shaded areas here, and then I recognize that the force acting on the lower half due to the upper half will in general have three force components: delta G1, delta G2, and delta G3. On the upper half, the forces will be opposite, Newton's third law. Now, with these quantities with the symbols available. This is how next three components of the stress tensor at point X is defined. So now I am talking about sigma 2(1), sigma 2(2), and sigma 2(3). Again, the first index in all the three components is being decided by the direction normal to the surface which has been used to cut the bulk into two halves through point P. And the second index corresponds to the force component. So now I have defined 6 stress components. For the next 3, now I will take the bulk of the fluid and cut it into two halves with plus minus E3, a plane which has unit normal along plus or minus E3 and going through the same point P. Yeah. So this half has its outward unit normal as plus E3. The other half has its outward unit normal as minus E3. The pictures are not perfect, but if you stare at them for maybe 10-15 seconds, you will be able to visualize what I'm trying to say. So this is the freshly cut surface, entire freshly cut surface. And it has its unit normal along minus E3 direction, going that side. Okay. Now, again, focusing on a small area with its centroid at P, we recognize that there are forces acting, delta H1, delta H2, delta H3, acting because of this half on this half here. And then Newton's third law gives me the directions of the forces that are acting on this due to this, the other half. With that figure as reference, the next three components are defined in this way. 3(1), 3(2), and 3(3). First index 3 because repeating the logic here. First index is 3 because the surface which cut the bulk into two halves has unit normal along plus minus E3. The second index tells us the force direction. So we have defined all 9 components of the stress tensor when our working coordinate system is Cartesian at point P. All the slides that I showed so far in the foregoing discussion, our aim has been to explain the meanings of the scalar component sigma ij with reference to the Cartesian coordinate system which we have been taking, frame fixed. Accordingly, we chose the bulk dividing planes to be perpendicular to one of the 3 basis vectors of our coordinate system, right? E1, E2, or E3. However, note that there exists a relationship between the local surface force vector, say delta T, which acts on a small area delta A, that exists on an imaginary surface created using a plane having its normal oriented along an arbitrary direction En. Okay. Let's have a look at this figure to understand what I'm saying. This is my frame fixed Cartesian coordinate system. So far I was making cuts. I was cutting the bulk either like this, or in a such that the unit normal was along E3. We need not do that all the time. We can cut the bulk into two halves by an arbitrary plane which has its orientation along En, and En is in general not E1, not E2, not E3. I can imagine a cut like that. Again through the same point P. Again I consider an area on that freshly created surface of the bulk of the fluid. Now on that surface, delta T could be the force vector exerted by the other half. On this half. This is okay. So I have delta T and En. There is a relationship between En delta T and the sigma as tensor itself. This is the relationship. You take a dot product of En, this unit normal that I'm showing on the right hand side of the slide. You take a dot product with the sigma tensor itself. That is, the physical meaning of that quantity would be what I have written here. Limiting value of delta T divided by delta A going to 0. Note that this quantity is a vector. Okay, you have a vector dot product with second order tensor. That will still be a vector. Okay, left hand side, and right hand side is still a vector because I have still kept delta T under bar. You can verify that all individual relationships listed on my previous slides when I was using planes which had unit normals along 1, 2 and 3 directions are special cases of this. So this is a more general relationship. If you want to relate force on a small area which has unit normal En, it can be accessed using the local state of the tensor sigma. Now let's come back to the motivation why we started talking about the stress tensor. My motivation was to be able to express the external surface forces acting on the mass that is currently residing inside the cuboidal control volume. Right? Previous class, we realized that the external forces can be divided into two parts, external body and external surface. Body force expression I obtained last time, assuming the body force to be the gravitational force, and this is what I needed. This is what I needed an expression for. Now what I'm going to do is, with stress tensor being defined, having been defined the stress tensor, I'm going to attempt expressing the external surface forces using various components of sigma ij, or derivatives, spatial derivatives of sigma ij's. And when I say derivatives, they will be at which location? They will be at the centroid of this control volume. And when I say various scalar components, again I am talking about scalar components of sigma at the same centroid. This is x. Mind you, the meaning of x changes from slide to slide, I mean depending on the context. When I have brought back my cuboidal control volume, x is the position vector of the centroid of this control volume. Whereas when I was defining stress tensor, pay attention, I was giving x position vector to point P, which is an arbitrarily chosen point in the bulk of the fluid, and I was trying to define stress tensor at a point. Okay, so the meaning of x on this slide is different from the meaning of x on this slide. All right. As I mentioned about 5 minutes ago, in reality, surface forces are always distributed on surfaces. They don't act at a point. In reality, they're always distributed. So if I have to talk about surface forces on this surface, they are distributed. It's a distributed force system, something like this. If you go to another surface, you go to this surface, the surface forces will have a distributed distribution. However, we, again the same reason, if delta x1, delta x2, delta x3 are small, we assume that the distribution is uniform on that face, and then we can replace these distributed force systems by one single force vector on each face acting at the centroid of the surface. That's what I'm showing here. So I am right now, this figure is about two surfaces, S1 and S2. I hope you are able to recognize, at least when you read the PDF, it should be very clear. S1 is a surface with outward unit normal E1 plus C1, and S2 is the surface of the cuboidal control volume with outward unit normal being minus C1. And then I am identifying C1, C2 as centroids of S1 and S2. C1 is the centroid of S1, C2 is the centroid of S2. Similarly, S3 and S4. In this figure, I'm talking about S3 and S4 faces, and I'm saying C3 is the centroid of S3, C4 is the centroid of S4. And finally, in this figure, I'm talking about S5 and S6, and the corresponding centroids of the faces or the surfaces are C5 and C6. Then I'm showing some arrows on these figures. Now these arrows are the surface force components that are acting on the corresponding surface. So for S1 surface, I'm saying that the surface force vector has these three components. And I have put those three components at the centroid, equivalent force system. On surface S2, similarly, I am putting forces in different, these are the three components of the forces that are coming in on S2 surface. We would like to write the expression of these forces in terms of sigma. I will do that in a little while, but before that, let's pay attention to this block here. I have written the coordinates of the 6 centroids. Coordinates of the faces, centroids of the 6 faces. Okay. C1, which is the centroid of face S1, has these coordinates. X1 plus delta X1 by 2, X2 and X3, where X1, X2, X3 are centroids written here. Go to C2, what changes? This becomes minus, x2, x3 remain the same. You go to C3, x1, then x2 plus delta x2 by 2. You are going here at the top. Delta x2 by 2 comma x3. C4, you go to the bottom side here. That's why you have x2 minus delta x2. Finally, C5 and C6 have the first two coordinates the same as the centroid of the control volume. It's only the third coordinate which is different, and that difference is highlighted here. Plus delta x3 by 2 for C5 and minus delta x3 by 2 for the sixth surface. All right. Now I'm trying to write the expression of surface forces using the stress tensor components. I put information about all the faces again on one slide, but let's focus. Let's take them one by one. Face S1. Let's talk about face S1. This figure. I am saying that face S1, on face S1, the surface force acting on face S1 has three components. One along E1, the other along E2, the third along E3. And those components have been written here. Now pay attention, this expression is loaded in the way that I am using index notation, sigma 1k ek. There is one repeated index, so this whole thing has three terms, the summation of three terms. Sigma 1 1 E1, sigma 1 2 E2, sigma 1 3 E3. I have written in a compact manner. I don't have much space on the slide. So on face S1, this is the force that is acting. What I have here. So that force has one contribution coming from area. What area? The area of the space, which is delta x2, delta x3. Area of S1. This is area of S1. Right? This is area of S1. So area multiplied by appropriate stress will give me a force. So what is the appropriate stress component? That is what is written here. Sigma 1k. 1 because the unit normal for this surface is 1. So that's how I choose it to be 1. But then the force can be in one direction, two direction, or three direction. And that's why k will take values 1, 2, and 3. And whatever value of k is taken here, that force will take its unit vector here. So it will be something like sigma 1, 1, E1, sigma 1, 2, E2, like that. Fine, but then there is another detail you must pay attention to, what I am writing as the argument of sigma 1k. So even though I am using the symbol sigma 1k as before, the argument has changed. So this sigma 1k is not at the centroid of the control volume, but it is at the centroid of S1. Centroid of S1. This is centroid of S1. Exactly this point. So I need sigma 1, 1 or 1, 2 or 1, 3, not at Q, at least as far as this expression is concerned. I need it at the centroid of the face. Okay, that's what I'm trying to express using this long argument here. Okay. Now you go to face S2. Face S2, like face S1, has area delta x2 delta x3. I'm also putting Ek here, and I'm also putting sigma 1k here, but then the argument has changed because now I'm talking about these values at C2. Centroid of surface 2. So that's why there is a minus sign here. Not only there a minus sign appears, a minus sign appears here also. Please pay attention to this. This is a place where we make a lot of mistakes. Why am I putting a minus sign here? I am putting a minus sign here because this surface has unit normal, outward unit normal along minus E2 direction. So the force that you get using sigma on a surface which has outward normal in minus E2 direction will naturally be pointing in the opposite direction as E1, E2, E3. But I want to get all forces along plus E1 plus E2 plus E3. Then only I'll be able to add or subtract forces correctly. Okay? And that is why this minus sign is coming here. So when you try to extract the relevant force components on a surface which has outward unit normal in a minus E1 direction, you use sigma 1k, but do put a minus sign. This is in accordance with the rules that I listed here, talking about these two rules. I don't know whether to what extent it is clear while I speak, but I want to put a marker in my video and in my notes here that please pay attention to this. If my voice is not clear, at least go and try to read the notes properly or some text, but make sure you understand the significance of this. It's not trivial putting a minus sign there. This minus sign holds a lot of importance. I have said enough. I don't have better ways to express. And as I said, if it is still not clear, at least I would tell you to take a pause and pay attention and try to understand yourself. So here it is plus, here it becomes minus. Going to face S3 and S4, which is shown here in this diagram. S3 has unit normal along plus E2, and that's why there will be a positive sign here. But face S4 has unit normal along minus E2, and that's why it will start with a minus sign here. Then it will have an area contribution, which is delta x3 times delta x1. I'm talking about this area and this area. And then I have stress components which have their first indices as 2. Why 2? Because I am talking about two surfaces which have unit normal plus minus E2. That 2 gets embedded here. This 2 gets embedded here. And then on that surface which has unit normal along 2, I have to take into account all the forces which could be in 1, 2 or 3 direction. 1, 2 and 3 direction, and those 3 directions are taken care by this K index here and here. So again, this is a summation of 3 terms. Forces in all 3 directions. Okay, then we come to the arguments. For S3, I go up delta x by 2, that's why I have this. For S4, I go minus for S4 I go minus delta x by 2. That's why I have minus here. A lot of signs and a lot of sign conventions here. Okay, so these are the forces on 3 and 4. Accordingly, along a similar line, force on S5 and S6, to get them, you need scalar stress components which start with 3, first index 3. Area is delta x1, delta x2. Found where? Found at C5 and C6. And then plus here and minus here. Same reason what I explained earlier. Okay. Now I have to simplify the expressions. Here it is still in terms of these arguments. I want to simplify the algebra. Let's focus on phase 1 and phase 2. Let's consider surfaces in pairs. I want to consider two surfaces at a time because many things get cancelled out. Same thing happened when I derived the differential form of RTT. Right? I considered S1 and S2 together, few things get cancelled out. Same thing I am doing here. I am trying to find an expression for F external surface, 1 and 2 combined. This 1, 2 means on S1 and on S2 combined, added with appropriate signs. I have expanded this now here. So K was repeated index. So I have expanded 3 terms, 1 term, 2 term, 3 term. This is the contribution coming from S1. And then 3 more terms. These are the contributions coming from S2 with appropriate signs. All right. Expanded form of what I have here. What am I going to do next? I am going to use Taylor series. Taylor series expansion. These pictures are the same that I had on the previous slide. Just I put it here for continuity. This is the new material on this slide. Truncated Taylor series expression. All spatial derivatives are at x1, x2, x3, which is the centroid of the control volume. So I know sigma 1, 1, 1, 2, all the way to sigma 3, 3. Suppose I know them. I want to find the value of sigma 1, 1 at centroid C1 here and at C2. How do I find it? This is how I find it. Sigma 1, 1 at C1 is sigma 1, 1 at Q plus this derivative, which is at Q multiplied by delta x1 by 2. First order approximation using truncated Taylor series. Similarly, sigma 1, 2 I want where? I want at C1. That is sigma 1, 2 at Q. And then this derivative of sigma 1, 2 with respect to x1 multiplied by delta x1 by 2. Similarly, sigma 1, 3. These three are for S1 surface. And then for S2 surfaces also we can accordingly find sigma 1, 1 at C2 in terms of sigma 1, 1 at Q, and then this extra term where this derivative is again at Q. We get a minus sign here, and then sigma 1, 2 at C2 and sigma 1, 3 at C3. These expressions you obtain. can see some of these things will get cancelled out, and that is why I want to consider these two surfaces together. All right, so you use these expressions and try to find this total external surface forces acting on the mass through surface S1 and S2. If you simplify the algebra, I have not shown all the steps, you must do it on your own at least once. Huge simplification. Starts looking compact, very compact. This is the force. External surface force on the mass residing inside the CV contributions from S1 and S2 only. S1 and S2 only. Three components matter here. 1, 1, 1, 2, 1, 3. Not surprising, because S1 and S2 have unit normals along plus minus E1. So they will get the force will get contribution from only those scalar components of sigma which has its first index, which have their first index as 1. That's what is happening here. Okay. Now once you have done the algebra and obtained this final expression, you can recognize a pattern and go ahead and write the contributions of external surface forces from S3 and S4 and S5 and S6 in this manner. What is the pattern here? This one was coming because of the fact that the unit normals were along plus minus E1. So when I go to S3 and S4, the unit normals are along plus minus E2. So I am going to make these first indices as 2. Okay. And then I recognize in this that this is 1 and this is also 1. I mean, this derivatives are also with respect to 1, and that is also making sense because I expanded Taylor series by displacing my position from the base location in plus E1 direction. That's why all derivatives were with respect to x1. But when I go to S3 and S4, I will have to displace my position along E2 direction, and that's why the derivatives will also become 2. And the third indices are actually about the force components. They will remain the same. Also note that here on the right hand side, I have the volume of the control volume, product of delta x1, delta x2 and delta x3. It just turns out to be like that. Once you use Taylor series expansion, it just turns out to be like this. So two of these factors come because of area, and one of this comes because of Taylor series derivative. Always happens like that. Accordingly, you can write the contributions from surfaces 5 and 6. The indices are as shown here.
Yes, sir.
Okay. So now we are in a position to assemble the entire external surface, entire external surface force, which is the same expression as the sum of these three things. I'm going to add them up. right? 6 surfaces contribute in total the sum of all these forces. So I will have 9 terms. Each one of them have components along E1, E2, E3. So on the next slide, I have rearranged the terms in a way such that the coefficients of E1 I have clubbed together, coefficients of E2 I have clubbed together, and similarly E3 I have clubbed together. That's what you will see here. So this is here E1, E2, E3, and each one is getting 3 contributions. So I have the external surface expression here. Then I go back to the full external force, which has one contribution from body, the other is from surface. The body force, you may recall, on Wednesday I derived that relationship to be this, which had density and components of acceleration due to the gravity vector. And then these things I just got from the surface forces, all added together. Interestingly, both contributions have delta x1, delta x2, delta x3 common factor, all of them. Okay. So out of this expression, now I can, using this assortment of terms, I can now extract F1 external, which will be what? Coefficient of E1. One contribution comes from this, and the other contribution will come from here. E1 is missing here. That will be this, and this combined will be called F1 external, one component of the external force. And then similarly, I can extract out the 2 component of the external force and 3. So you extract those components, and then I am now in a position to go back and complete the governing equation of the velocity vector. So if slide number 8, lecture 15, I reached up to this point in my quest to get the equation for V, and then I took a pause. I said that I need expressions for these forces, right? Then I talked about body force, then I talked about stress. All have been completed now, and now I am in a position to replace these things in terms of sigma or its derivatives, stress or its derivatives, or body forces G1, G2, G3, borrowed from here. Notice that there is this product or the volume of the control volume in the denominator, whereas here it is in the numerator. So this is going to get cancelled out. Similar situation what happened in the continuity equation and what I described in the beginning of this class. I start with the control volume, but the characteristics of the control volume vanish, giving me an equation which involves quantities only at Q, only at the centroid of the control volume. The dimensions of the control volume do not matter. Okay. These are the 3 equations of V1, V2, and V3. Where on the right hand side, I have replaced the external forces in terms of the body forces and stress tensor. Complicated equation. Algebra wise, it's complicated. Solution wise, it is immensely complicated. At one point, I will talk about the challenges that this equation has posed to the entire research community in the history of science, one of the most difficult equations to handle. I'll talk about it in detail later. But for the time being, at least notice that I have obtained 3 new partial differential equations. The second question is, what is sigma ij after all? It's just a new symbol. Of course, it has a physical meaning. It has force per unit area. But who will tell me sigma, what sigma is? That question needs to be answered sooner or later. What is the relationship of sigma with the velocity field, if at all there is any relationship? We'll answer these questions soon. For the time being, I want to simplify. I'll take 5 more minutes. For the time being, let us simplify the equations further. Algebra wise, we will try to make it appear simpler. And that will help me and explain some physical aspects of these equations. Recall on slide number 1, lecture 15, in fact on slide number 1 of lecture 16 also I wrote this equation, which is the continuity equation, right? I am going to use the continuity equation to simplify the left hand side of these equations a little bit more. How am I going to do it? So this is the continuity equation derived in the last class. Okay. I call this equation number 1. And then there are the 3 velocity equations that I got. I call them 2, 3, and 4. I'm going to do a manipulation, algebraic manipulation, which is symbolically written here. I'm going to take the first equation, which is the continuity equation, multiply it with V1, and then subtract it out from the second equation here. Okay. I have shown some steps here. So if I just focus on this term, partial with the time term, I'm saying that I take the second equation, partial with time, right? Del t of rho V1, and I subtract out the product of V1 with this. I get this. V1 times del rho del t. Now if you apply product rule of differentiation, this simplifies to rho del V1 del t. Right? Then I focus on the second group of terms here. In the continuity equation, this is the term, and in the V1 equation, this is the term here. I'm going to subtract V1 times this from this term here. That's what I have written here. Again, applying product rule of differentiation, you will get this. Same thing if I do if I manipulate these two terms, what will I get? I will have del x2 rho V1 V2 is coming from 2 equation minus V2. This time I'm going to, just V1 actually. V1 times del rho V2 del x2. What do I get here? I should get rho V2 del V1 del x2. Right? And then I focus on this term here and this term here. I do del x3 of rho V1 V3 minus V1 del x3 rho V3. I get rho V3 del V1 del x3. Right? Then I move forward and I look at the right hand side of equation number 1. It has 0. So if I multiply 0 by V1 and subtract from the right hand side of this equation 2, nothing changes. Right? So nothing changes on the right hand side, but the left hand side I have simplified things a lot. Okay. So if you follow that simplification that I did, the resulting equation that we get is this is the resulting equation, which has been obtained as 2 minus 1 times V1. Okay. Why have I done this simplification? Notice that with this simplification, I can write the left hand side as this is the left hand side. Right? What is nice about this left hand side? Nice thing about this left hand side is it has an operator we are very familiar with. Advection operator has come on the left hand side. And there is a partial with time also, so I can write this as dv1 dt. So my v1 equation looks somewhat simpler than the previous one. Compare this equation here with this equation. I hope you will agree that it looks simplified. Not only it looks simplified, but the operator that is there on the left hand side, I have a very nice, clear, crystal clear meaning of that, physical meaning of that operator, which is v1 dt is what? Acceleration, one component of the acceleration of a fluid particle, which is at the centroid of the control volume currently. And we are getting an expression for that acceleration. And that acceleration must be the net force acting on the fluid particle. Indeed, the net force is there on the right hand side. One force is the surface force contribution, the other is the body force. So after so much algebra, we are finally getting an equation which is going to help us understand the physics of how the particle accelerates, the fluid particle accelerates. I'll talk more about it in the next class. Let's stop here now.